Right, so nice. So today we're doing a past paper, which this one was my past paper, because when I did it last year, this was the past paper. The questions outdated, but it's now outdated because it's the same question from the tutorial, just changed up a little bit. So it's the same tutorial. So the questions not on outdated too much. So we have the first question on this side, and we will run it through. And as usual, if you have any questions, send me chat. Don't mind answering. So I read in your head. A global company that manufactures smartphones has five manufacturing plants located in USA, Brazil, China, Singapore, and Sweden. And these produce 20, 30, 25, 15, and 10%. So our percent. So I now have to convert that to a decimal value, right? Respectively, of such devices. Okay, so they have five stations at different production levels. Okay, suppose that the probabilities that a smartphone manufactured by these plants is defective are, well, they give you the percentage. In this case, they give you decimals. Get true, respectively. Okay, so you have five production plants. Each have a probability of production, or the tell you the um, percentage that each plant produces of the total output of the company, and they give you the probability that an item could be defective that is manufactured from each plant. Alright, so this here straight from the tutorial. The concept is the same. So anytime they give you multiple different things and each of them are related to the previous one, this is conditional probability. Yeah, this how this phrase is conditional probability. All right. So one thing I love to do is draw up a tree diagram, which will outline all the possible probabilities that you need, and I will literally just outline the whole question for you, so you don't have to stress out about too much stuff. Yeah. So we start with our branch. So this here is the product. We can say production. You don't need to start with this, but I just like to start with it. All right, so we have five. So we have one, two, we have three, four. So we have one here, two, three, four, five. So that's your five outputs. So you have USA up here, and I think they said Brazil, then they said China, Singapore, and I drawing that whole thing. And then they said Sweden. Nice. And then they said the production of each. So they said respectively. So in the order, it is the order of each. So 20% is 0.2. Brazil is 0.3. Then China is 0.25. Singapore is 0.15. And Sweden is 0.1%. Well, 0.1 is the probability, not percentage. That's converted. So the next piece, or with another different color, is the piece that they're talking about with the defective. So we have each production. Now they gave us the percent, or you could say the probability of a product being defective. So okay, drop the probabilities, or you could say possible options. So this here is defective, not defective. Defective, not defective. Defective, not defective. Defective, not defective. Defective, not defective for each plant. So they said the probability of it being defective from USA, this was 0.01. For Brazil, it was 0.05. For China, it was 0.02. For Singapore is 0.03, and then for Sweden is 0.01. And because we know the probabilities how to add up, so one in each branch, if the defective is 0.01, not defective will be 1 minus 0.01. So here will be 0.99, here will be 0.95, here will be 0.98, here will be 0.97, and here will be 0.99 again. So at the end of it, that is the last decision they gave us. So we have here and probability. So probability at the branch. So the little arrows to show that you finish. Nice. So let's write out what each of these branches tell us. So this here telling us, so you always multiply on the branch, right? So there's the probability of it being defective and USA. Okay, that's multiplying, and there's a U, not a V. So here's the probability of not defective and USA. Here's the probability of defective and Brazil. Here's the probability of not defective and Brazil. Here's the probability of defective and China. Here's the probability of not defective and China. Here's the probability of defective and Singapore. And here the probability of not defective and Singapore. Here is the probability of defective and Sweden. And the last one, the probability of not defective and Sweden. So that's what you have there for all the branches. Okay, that's multiply. When you multiply probability, that is when you add is O. So that is why I said and why I use U, because the upside down, which is the N, so saying U, the N is intersection, which means and. The U is union, which means O. So I hope I clarified that. I keep mixing it up. Anyway, so we can multiply each branch and get the number one time. Because this would like save us heck loads of time in the end of the question. So this will be 0.2 by 0.01. So put in a calculator. I am not feeling like going through all this. So because of time, so I just write the value. This one is 0.3 by 0.05. This one here is 0.3 by 0.95. Here is 0.25 by 0.02. This branch here is 0.25 by 0.98. Here is 0.15 by 0.03. Here is 0.15 by 0.97. Here is 0.1 by 0.01. And the bottom here is 0.1 by 0.99. Alright, so that is your probabilities for all your branches. You have literally everything you could possibly want here, with an exception of one thing. So that is the first piece. So we draw that first. So all this is for part A. We're in the part A as yet. So part A now, the ones. If a smartphone from a company sold at a retail shop is likely to come from any of these manufacturing plants, what is the probability that it is defective? Well, hear this. For it to be defective, it could either, hear me out here and talk slow. For it to be defective, it could either come from here, or here, or here, or here. I think I'm missing one. Yeah, USA. Or here. So here, or here, or here, or here, or here. Not as saying or. because that's for a reason. So since it could either come from any of these plants here for it to be defective, but I would ask. The ask if I see something defective, what is the probability of being defective? Regardless of the plant. I just want to know what is the probability of it being defective. Because I was asked so. They never say given that it come from anywhere, they just say what is the probability of it being defective? So it will just be the addition, the sum of all these here. So you can say the probability of it being defective is the probability of defective and USA plus the probability of defective and Brazil plus the probability of it being defective and come from China plus the probability of it being defective after China is Singapore. And then the last one is plus the probability of it being defective and it come from Sweden. Yeah, so just be this plus this plus this plus this plus this and again. Alright, so the answer, I sent you the document already with this, so I don't need to like do the values. So let's go into how the thought about it, right? So all in all, the answer it should end up with 0.0275. Yeah, so that would the document have. And then when you work it out, you get the same value, right? In other sense, you come in here to do arithmetic. So that's the first part, right? Part B, they said if a smartphone selected at random is found to be defective, okay, what is the probability that it was manufactured by the following plants? So they give you a condition here. Yeah, so they give you a specific condition that you have to adhere to in this case. So there's conditional probability, right? So for conditional probability, the probability of A given B is the probability of A intersect B divided by the probability of B. This is for conditional probability. There's the equation. Because if you read the question, you notice that they gave you a condition. Given that. What is the probability of it being from USA, given that it is defective? That I basically what I asked you. If a smartphone is selected at random, it's found to be defective. So it is defective. I want to know what is the probability that it came from all these plants. So you have, and be careful, in the question you have this here. The tree diagram, or however you want to call it, does give you this numerator value here, the ants. That is here, that's multiplying the branches of the tree. But what you don't have, or we won't have from the tree diagram itself, is this. So you have to be careful. Let us go and pluck out what the tree diagram have. But the tree diagram have the ants, not the conditional probabilities straight off the bat. So to get the conditional probabilities, you have to divide by the sum. So in this case, how we will write it is the probability of it coming from USA, because that's what I asked for, given that it is defective. Yeah, so I want to know where's the probability that it came from USA, given that it is defective. And I want to know that for all the others. So that will equal to, so using the same concept, so it will be the probability of USA, right, intersect with it being defective divided by the probability of defectiveness. Yeah, so in this case, 0.01 is the effectiveness from USA. So if you want to probably write like that, put given, so you can say the probability of defective. So probably USA intersect with the probability of defective, yeah, given that is from USA. But it is for USA. There's not just the probability of it being defective across the board. That's for defective for USA, which is basically this value here. It's the same thing. So I'll write it here. So before I write any value, I'm going to write how it will look when you expand it out. So basically here, this will be the probability of USA multiplied by the probability of it being defective given that it's from USA. That's what it is. This here is basically the same. It's the same thing as this, which is the same thing as up here. Same value. Same value. 0.2 by 0.01. Right? It's the same thing. That's when you're writing it out. Write it like this. Because what I do want you to do is this. I'm going to show you what I do want you to do. So I do want you to write this here, and then down here, if you want to split it up, go and write this. Well, that's the probability of D alone, and divided by the probability of D. Because that's wrong. Because I don't want you to use the probability of D that you get before. I will throw up your whole answer. So when you're doing this, write this in the correct way. So it's specific. So it is defective. That's good. That's okay. But where it is defective. How to come from you. It's not defective on a whole. Alright, and this down here is the same idea. So be careful when you're doing it. So given that it's from USA. So this value here is basically this value here. And then this value here is basically this value here. Right? If you want to, you can literally just take this. I want to make sure, just in case I don't want to split it up. So you gotta just stop here. So anyway, so this here would have be 0.2 by 0.01 divided by the probability of it being defective, which I calculated already, or which we did. So it would be 0.0275. And that will give you 0.072. Short 3 decimal places. So let's try one more. So probability of it coming from Brazil, given that it was defective. So it'll be the probability of it, Brazil, intersect with defective, given that it was from Brazil, divided by the probability of it being defective. So the probability of it being from Brazil is 0.3, and the probability of it being defective, given that it came from Brazil, is 0.05. So it could just be the product of these two. Beauty of doing the tree diagram is here already have the value here. Yeah, so it helps you out a lot. So that was 0.3 by 0.05 and divided by the probability of being defective, which is 0.0275. So then you know how to do for the probability of it coming from China, given that it was defective, the probability of it coming from Singapore, given that it was defective, and the last one is the probability of it coming from Brazil, given that it was defective. Oh, I do that already. Okay, cool. I want to done on top. So, and that was that question. So when you're doing these, you have to read the questions slowly and make sure you're doing the correct thing, because an easy mistake people might have say is the probability of it being defective, given that it came from somewhere else, and you might have throw off your whole answer. The ones if a defective came from Brazil, given that it is defective. Probability of it China coming from China, given that it was defective. That's what the question was asking for. So that's how to be careful how we're doing it. Right, and that was that. Okay, so now part C. So the reliability of a smartphone depends on the effective working of a number of subcomponents. Assume that these subcomponents fail independently and that the probability of failure of the subcomponents I is Pi. So the probability of failure is Pi. Consider the reliability model of the smartphone system in terms of the subcomponents in figure 1, which is this here. Alright, we'll go back down to that just now. Determine the probability of failure of the fast smartphone in terms of this. Okay, so with respect to here, there's our circuit. So you enter here, you exit here. Some pathway you use, go and get it to work, obviously. So the first thing we had to do, right? You can just work the question, like if you're trying to get it to work, and then the probability of failure would just be 1 minus the probability of it working, if you were to fail. So the probability of failure is 1 minus the probability of success, or it working, right? So our goal right now will be to calculate this. Because once you have this, 1 minus that will give you success. So that's what we're trying to work towards now. So just like I told you before, right? When it's in series, you multiply, or when it's in parallel, you add. It's the same concept you will have to use here. Alright, and then I'll write that down here because we can just move the question from here. So when you're doing these type of questions, so if something in parallel, just put this here in terms of probability. So when you're doing it, which is the same for, so you can say S, I, so it's S2 and S1. That kind of easy. Right, so you let E be the probability, or you can say let it be the event of success, like event that Si functions. So it actually working. So the probability of it working, which is E, the I just means the index. When it's in parallel, alright, so that would just be 1 minus all from n is equal to 1, or in this case I, that is the index we're using. So I is equal to 1 to n of pi. Oh well. Yeah, so that's that one. And then when it's in series, so the same, let E be the events. So S1, S2, Si functions. So probability AI. So when it's in series, so it's the same going across all indexes. I is equal to 1 to n, but in this case is in the bracket itself is 1 minus pi. So the difference is this one here, the index in here, and the 1 minus t, which is when it's in parallel. But in series is 1 minus the probabilities of each of them. Yeah, so you'll see when we do the question. But this you have to remember when you're doing these types of questions. So When it's in parallel, it's just 1 minus all of them, and this one, the 1 minus inside the brackets, and the summation, or the summation by the index part outside. So let's leave that there and run through the question. So the first thing we do, just treat this like a normal circuit. And you're just trying to get the Boolean expression fit like normal. Alright, so if I start here, I have two ways I could go. I could go through S1 and S2 to get out, or I could go through S3, the parallel combination of all these to get to the outside. So it's in parallel, and you have some series elements inside of it. So you kind of seeing the event that going on here. So the first piece, like work like normal Boolean algebra. So in this case, you have P, sorry, here. So you have P1, 2. So you can say P1 and 2 because it's in series. So that is there. Plus, because it's in parallel. So you have P3 and because it's in series with this combination here. So for now, you could write all the numbers. So it could be P3 and P4, 5, 6, 7, 8. Yeah, we really care what the rest is. So this will be the probability of it working. So we have 1 and 2 plus 3 and all this here. I will put it in our bracket. So we have this one here. It's not really difficult to do that one because it's a series. So this would have be P1, you can say PS1, keeping the same thing that I have there. I gotta change it. So it'll be PS1 multiplied by PS2, just in a bracket. And then we have this piece here, which we don't know as it. So you have to calculate it outside. So you can say P3 and P4, 5, 6, 7, 8. And I go through that. So this one here, this in series. So it will be PS3 right? And then you have this here. So you have what will be? So plus maybe PS4 by PS6, put in a bracket, plus this piece here, PS5 by PS7, plus, and I just PS8. So that's a recap. So you have this here, this in series, so you multiply, which you already have here. And then this piece here in series, but you have a combination here that's in parallel. So it'll be a S3 that you had before, multiply, because I multiply by this here. So it'll be PS4, PS6 plus PS5, PS7 plus PS8. And that's what we have here. So putting everything together now, just trying to save space. So the probability of success, which is what we have here. You see how small I could write it. So you have PS1 in series with PS2, so that will give you a particle to n, and then it's in parallel, so plus, and now we have PS3 in series, so multiply by the parallel combination of PS4 in series with PS6 plus PS5 in series with PS7 plus PS8. So that is the overall part here. Alright, so now what we need to do to finish the question, we have to use this that we'll be trying to get down here. So all we did was just get the Boolean expression for the circuit itself. We didn't really do much in terms of the calculations itself. So when it's in series, it's 1 minus pi, and in parallel, it's just 1 minus the sum of all of that. So what we could do now is just run it. So remember, pi is the probability, right? So to finish it off, pa, so these two, it's in series. So we'll use this one down here. So it'll be 1 minus P1, 1 minus P2, and then it's in parallel, so plus, and this in series, so 1 minus P3, sorry, PS3, watch that. I keep the same thing, that's P3, that's P3, don't know how complicated, right, P3, then open bracket, I have a next series combination here, so it'll be 1 minus P4, 1 minus P5, P6, sorry, then plus 1 minus P6, P5, sorry, P4 and P6, this was P6, then P5, and 1 minus P7, and then this here is just 1 minus P8. Right, so that is the probability of success that functions. And the last thing I had to do, so as I said before, the probability of failure will just be 1 minus the probability of success. So that will just equal to 1 minus, let me just write over everything I had there before. 1 minus P3 by 1 minus P4, 1 minus P6 plus 1 minus P5, 1 minus P7 plus 1 minus P8. Yeah, that's the answer. So let's run it through one more time. So you have the circuit here. The first thing you do is you get the Boolean expression flip. Just get the Boolean expression. So this series you multiply, it's in parallel with S3, so you add, so it could be open bracket S3 multiplied by this parallel combination, so it could just be this in series plus this in series plus this, which is this piece here, and you get back to home. The next thing you do is you use these two relationships down here. So if it's in series, it's 1 minus pi, when it's in parallel, is 1 minus all these here. Alright, so you can do it for each. And then finally, the one in probability of failure, because we're working in probability of success, so it just be 1 minus the probability of it working, so the probability of success. And that would be the answer. Right, that's all it is. That's really just using. Right, so that was that. Okay, so we reach number 2. Okay, so number 2, I read in your hearing. I make a statement for moving too fast by the time. So a noisy communication channel has a per digit error probability P of 0.01. The source emits symbols that are encoded 8 bits at a time there is a symbol error when at least one of the bits representing the symbol changes. Okay, there is the probability that multiple bits can change at the same time due to the noisy channel. So let x represent the random variable, which is the number of bits errors in a given symbol. Okay, calculate and plot the probability mass function of x. So this question here is a distribution, but we don't know what distribution it is. So just go through, rattle through any post-up. Then they give us interval in terms of time and space. No, they didn't give us an interval. And there's normally word it in a certain way because lambda is the average amount of occurrences in the interval. So they never talk about average, never talk about any intervals or anything like that. So it can't be possible. The key word that sell it out is average, like the average amount of stuff, or if they give you an interval of time or space. So it's not that. We know it's not normal because it's not continuous distribution. Alright? So, and we know it's not uniform because the probability of 1, 2, 3, 4, 5 bits changing is not the same. Alright? So, by elimination, how to be binomial. Another giveaway is that I want to know the amount of successes, which in this case would be the number of bits flipped in n. So they're sending 8 bits, and I want to know the probability that 1 might flip, 2 might flip, 3 might flip, 4 might flip, so on and so forth. So that had to be binomial because I want to know the amount of successes in n trials. N in this case is 8, and p, can I give you p, which also give it away, is 0.01. Remember the parameters for poisson is lambda. Right, so then get your average occurrence in a certain amount of time. It can't be that distribution. Yeah, so binomial, majority of the time will be binomial. She wouldn't really bring a, she could bring poisson, but the wording of the question will be totally different. She wouldn't give you a P for lambda, for poisson, and them kind of stuff. She'll normally phrase it in a different way. So that's that. So the said first part, calculate and plot the probability mass function. So the probability mass function is PDF is the same thing. So you normally say PMF for discrete and PDF for continuous. But the PDF, PMF is the same idea, just worded different. So if you see PMF for PDF, it's the same thing you have to do, but normally just use PMF for discrete and PDF density function for the continuous. So we know this is discrete and we know it's binomial. So the next thing we have to do is calculate all the different possibilities that you can have. So they already said x is the number of bits in error in a symbol. Alright, so then now they said we know x follows a binomial distribution and the parameter n is 8 and p is 0.01 as given in the question. Straight off the bat. So the first thing we need to get the PMF. So the different probabilities or the different stuff that we could get. We could get 0 bits flipping, so that would be the probability x equal to 0. We could get 1 bit flipping. We could get 2 bits flipping. 3, we could get it by now straight down to 8, which I may not have enough space. So I'll zoom in. 4, 5, 6, 7, and last one in space 8. So 1, 2, 3, 4, 5, 6, 7, 8. So 1 bit could flip, 2 bits, 3 bits, 4 bits, 5 bits, 6 bits, 7 bits, and all the bits could flip in the symbol of 8 bits. Yeah. So if you get 0 successes in n trials, 1 success in n trials, 2 successes in n trials, 6 successes in n trials, same thing, binomial. So we know the equation for binomial is n, and here x, and is equal to n factorial divided by n minus x factorial, and then you have x factorial. Alright, but you don't really need to worry about this because you could just do the combinations in a calculator. Yeah, so you don't stress out too much about it. So I just going to erase that. I don't care about that. But if you want to, you could use it, but you have a calculator there, so just do it in a calculator. Alright, so the equation for this here, for the general piece, I'll write it on top here for the binomial. Where's my oh, by AA, okay, no problem. Sure, no problem. Yes, you don't like me today. So just n x multiplied by p to the power of x by q to the n minus x. And there's the probability x is equal to x. So this basically we're going to be using over and over and over for all of them. So I'm going to just do like 3 and you can try this because you already had the solutions. So here, this will be the probability x equal to 0. So it'll be 8 and x 0. P, in this case, P is 0 0.01 and x is 0. And Q would just be the remainder from P. So remember, Q is just 1 minus P. Yeah, because Q is failure in this case. So it'll be 0.99 by n minus x. So it'll be 8. So you have 8 failures and 0 successes. Now, plug that in a calculator. So you get 0.92. But add a decimal, but we keep that to 2 decimal places. So the other one is 1. So it'll be n1. Success is 1. So it's p to the power of 1 by q to the power of n minus x, which is 7. So you end up with 0.074. And the last one, I'm going to do 8, 2. Success is 0.01 to the power of 2. Failures is 0.99. N minus x, 8 minus 2 will be 6. And the probability for that one will be 0.0026. And you just repeat the same concept for all of them and you get your answers. Alright? So with that done, you will have your PMF. So what did you do for your PMF? You already have all the probabilities and you already have your x's, which is your number of bits flipped. So you have 0, so let's say 1, yes, because 0 could be here. 2, 3, 4, 5, 6, 7, and 8. And you have each probability, so you just sketch it. However it looks, it's just a sketch, not drawn to any scale. And this would be a PMF or PDF, however you memorize it. So that's the idea. So you use the equation, calculate the probabilities for each value in your set, and you have 0 to 8, and you will have the calculated probabilities for each, and here just sketch it. So you will have the value, so you will know which line higher or lower or whatever, and that would be a PMF. Alright, the next thing you have to do, which you could use your PMF to get, is the cumulative density function. Remember, this here is the probability that x is less than or equal to a specific value x. Once you remember that, you could get anything. You already have the PMF. Once you have the PMF or PDF, whatever, you could get the CDF straight from it. So same x. So x values are the same. So you have 0, 1, 2, 3, 4, 5. No, use too much room. Erase that. Small up the space. 1, put 2 here. 3, 4, 5, 6, 7, 8, 9. Okay, we ended at 8, but I went over. So here's the probability that x is less than or equal to x, right? So 0. What is the probability that x is less than or equal to 0? Well, in this case, they gave us it here. So remember, it's the probability that x is less than or equal to 0. So in this case, it's starting at 0.92. So this one here is going to be horizontal lines. All right, and then the next one is the probability that x is less than or equal to 1. So you n here. So less than or equal to 1. So you see here now. So you have to add up this with the 0. So back to our thing. So you have to add this here to this because it's less than or equal to. Right? So that will be that piece there. So you just keep on going up with the same value you have here, then less than or equal to 2. You go here, so you add up here, here, and 0. So 2, 1, and 0. And you just keep going across. Less than or equal to 3, so it'll be 3, 2, 1, 0. Less than or equal to 4 will be 4, 3, 2, 1, 0. Less than or equal to 5 will be 5, 4, 3, 2, 1, 0. Less than or equal to 6 will be 6, 5, 4, 3, 2, 1, 0. 7, same thing, and 8 will be less than or equal to 8, 7, 6, 5, 4, 3, 2, 1, 0. When you add up all of that up, you're supposed to get 1 at the end of it. So you just keep on with your stairs or whatever, and the last one will just be 1, because the sum of the probabilities must equal to 1 at a particular point. But that is the concept right there. Okay, if you use the PDF to get your CDF, because there's the probability that x is less than or equal to a particular value. Right? So your sum should always end up being 1. If it's not ending up being 1, you do sum wrong. So right here, okay, run your CDFs if you want to. One time, you can like do all this in a table. So you can have the probability x is less than or equal to x. So here, here's 0.92. So here will be 0.92 plus 0.074. And here will be 0.274 plus 0.0026. So we get like 0.9999. And you can just repeat the same for everything. And if you get your CDF values one time, yeah, and that's it. Solution any slightly document. So any document you will see the user binomial coefficients, Pascal's triangle diagram. You don't need to know it. It would be just wasting time doing it. You could do it if you know it, but you could just do the values in a calculator. Right? To me, it really makes sense doing it because you have the calculator. Alright? So analyze that. So the next one is easy. The mean, which is the expectation of x, is n by the probability, so it'll be 8 by 0.01, and then the variance of the axis for that will be n p q, or if they didn't give you q, it would be n p by 1 minus p, because 1 minus p is q. Alright, and then the last one, they said find the probability that there will be at least, so you're right, the probability that x will be at least 3 bits in error. So they never said less, more than, or equal to, they just say it will be at least 3 bits in error. So more than or equal to 3. Because I would ask it for basically. So it could be 3, 4, 5, 6. So at least. At least. So this here, you could go and add. So more than or equal to 3. So it would be 3 plus 4 plus 5 plus 6 plus 7 plus 8. You can do all that. Or you could carve out where you don't want. So in this case, it will be 1 minus the probability that x is less than or equal to 2. So that basically what you'll be carving out. In maths terms, it would just be 1 minus the probability x is equal to 0 plus probability x equal to 1 plus the probability x is equal to 2. Alright, and you'll get the answer there. Alright, and that's that. So I have a call coming, let me just take it. Finish it. Alright, so that was the discrete random variable question. Alright, so that was that. Once you get a PMF, you can get a CDF. Because once you remember, the CDF is just the probability that x is less than or equal to x. That's the concept. You just plot the diagram. The answer's in the document, so you can go ahead and get it there. Right, so if this confusing you, so how I just remember it? Remember discrete, right? So it doesn't really have any values here. Yeah, so just treat it. Do it like if you're doing a discrete for the PDF in terms of the vertical lines, but just know that it's gonna be that value straight until the next one. So here was less than or equal to 0, right? So this value here was like 0.922, whatever. I think it was what we had get it. Yeah, this value here. Because remember, less than or equal to 2 is 0 plus anything before that. So it will just be 0. So you can start at 0.92. And you can stay that value until, and then you reach 1. Then at 1, it could be probability x is less than or equal to 1. So you basically adding the probability at 1 to the probability at 0. And you end up with this up here. But this here is the change. So this here is the probability x is equal to 0 plus the probability x is equal to 1. That little rise there, that is what that is. So the rising up to here, and it will stay that value until 2. And then here now is your rise. So this rise will be the probability x is equal to 0 plus the probability x equal to 1 plus the probability x equal to 2. And you just keep on going up, going up, going up, going up. And you're just going to be adding up all the values. So for this part here, for it to reach 1, it basically had to be the probability x equal to 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. And all added up together will give you 1. Alright, which should be this last rise here cumulatively. Yeah, and that is how you think about it when you're doing for discretes. So all here could be whatever zeros. All here could be 1. All here could be less than or equal to 2. All here could be less than or equal to 3. And you just keep on going up. All here could be less than or equal to 8, which should be 1. Because 8 is the last value in your data set. Alright, so I hope that helped. And run through this one here. read it carefully and see where you could carve out where you don't need. Right? Alright, last question, which is basically question 21 in the probability tutorial. So she brought it for them in this midterm. She may or may not bring it for you all, so it's tough. So anyway, so they said a noisy um, voltage source has a Gaussian distribution of positive mean mu and variance sigma squared. So X follows a normal distribution with parameters with the mean and you have your variance. Right? So we know that from the parameters itself from the notes. So they said write an expression for the PDF. No, they say PDF here and a PNF, they talk about continuous of the output voltage of the noisy source. Okay, so write an expression. So when you have one expression for the PDF of a normal distribution. Alright, so that is the pro f of x is equal to 1 on the square root of 2 pi sigma squared by e to the minus x minus mu squared on 2 sigma squared. That is a PDF for your normal distribution. Don't know why that's 5 marks. Alright, so that is that. I don't really have much more to it. I have no idea why it's 5 marks. That is the expression. Alright, so then part B. Now, this says sketch and annotate the PDF of the output voltage of the noise source. Okay, so we need to draw a bell-shaped curve. So 1 mark, it's centered at your mean, like 1 mark there. Then your standard deviation, like say variance, is how it deviates from the mean. So you can like just write an arrow, right? And this is your standard deviation. Okay, and that's that. Don't really have much there. That's it. If you want to, you can write back here 1 square root of 2 pi sigma squared e to the minus x minus mu squared on 2 sigma squared. What has that? Mean, variance, the bell-shaped curve centered about your mean value. And the last thing that you'll get marks for is your axes. So this here is f of x, and down here is x. Right? So that's that. So bell-shaped curve. So now part C. Derive and sketch an expression for the CDF of the voltage of the noise source. Okay, no problem. So this sketch is the same no matter what you're doing. So this is the CDF of a continuous random variable. So the mean 50% of the data set here and 50% here. That is why it's centered about your mean value. Yeah, so how the graph will look is, so up here is still capital F of x, or the probability x is less than or equal to x. Here is still x. But think about it, if x is 10, half of that will be 5. But if you're plotting the CDF, you know 50% will lie above 5 and 50% will lie below 5. So you can use that same concept. Remember, it's still adding up to 1. So half will be 0.5 and 0.5 will be at whatever value that is half of your x. So it will look as, and this is your 1 value. So it will go through like normal, like a little curve, starting at 0. So it will go up, and then it will approach the line, but it will never touch it. It will kind of plateau, it will go real close, but it will never touch this because your bell shape, it goes from positive infinity to negative infinity. So it never actually touches, because infinity and negative infinity are concepts. So it doesn't really touch. It literally just floats. So don't draw this touching. You can continue going high, but don't touch it. Just let it plateau. But it never touches. It never really reaches. Same thing for down here. It will never reach zero. So it can just go up, almost touch, and that will be a CDF, the expression for it. So in order to get the CDF, you have to integrate the PDF. So that is where you got this from. So the integral of the PDF will give a CDF. So just integrate the PDF. We already have a PDF. So capital F of X will be the integral. So remember, it's less than or equal to a particular value. So in this case, it will go from whatever the value is down to minus infinity. Remember, this is continuous. So of f of x dx, so that is equal to 1 on square root of 2 pi sigma squared by the integral from minus infinity to x. So less than or equal to x will be from x to minus infinity, right? So e to the minus x minus mu squared on 2 sigma squared dx. Alright, so here now back to the CDF. Our next piece I could write, if you remember, is that this part here is mu. Yeah, because mu, everything less than mu is 50%, and above mu is 50%. You gotta write the 50%. What is the idea? So when you plot in the CDF, you have your axes, x, capital F of x, you have your 1 line is 0.5 line, and you have mu, which is half. So you go through, plateau, but don't touch the 1 line. And that is it. So kind of, alright, so that is this here. And we have this. So this is actually the answer for C. Sketch and the expression. And then the last, well, second to last one. In terms of the complementary error function, derive an expression for the probability that the noise voltage exceeds some positive threshold. So they're talking about the complementary error function if C and if. So you remember if x is 2 roots pi, right? So it's 2 root pi integral, and if, so if you center that's 0, you can say mean, you have if here. So if is from that mean to x, and then if c is from x to infinity. And remember, it's symmetrical. That's where I get the 2 from. Minus x minus infinity. So the question asks us, well, I kind of gave you the answer, the complementary error function. Derive an expression for the probability that the noise exceeds some positive threshold. Okay, so in this case here is a on 2. So we're talking about this here. It exceeds a particular value, right? So that's what we want, basically. And what I'll write in if c, so if is minus t squared dt. So this does go from, in this case, mu to x. So I could go from 0 to x. That's how the definition has it. 0 to x, but we're just going from your mean or whatever the value is up to x. And then you have c of x, which is 2 on root pi integral. So this integral going from x to positive infinity, right? And then that will be e minus t squared dt. So these are the two types of errors or error functions there are. So let's go through. So it's the same proof I went through last week. So you can just memorize these steps for it. So first thing we will do is write the probability that they want. So they want the probability that x is more than a on 2. So to get that, we have to integrate the PDF from a on 2 to positive infinity. So of the PDF dx. So we had to do. Remember, to get probability is the area under the graph. So we have to integrate the equation of the bell-shaped curve for the normal distribution. So that'll be 1 on the square roots 2 pi sigma squared integral a on 2 to infinity of e to the minus x minus mu squared on 2 sigma squared dx. Nice, so we have that. The second step, what we need to do, we kind of have to manipulate it. Same steps we did last week. We need to manipulate it to get this to look like this. So the t squared, right now do have a t squared. dt, the dx are the go. 2 pi, real thing at happen here. So that is where all these steps will get you to. So the first thing we could do is get rid of this to get in terms of t squared. So we could say let t squared equal to the big piece up there. Note I never remove the minus because I kind of need it. Because when I compare it, both of them were minus. So you just remove t squared and keep the minus. So you square root both sides. Okay, you want to get rid of the square. So t will just equal to x minus mu and the square root of 2 sigma. But the square root of this piece here, the square root of sigma squared is sigma. Square root of 2 is root 2. So we have this here. So what we're working towards here is to get dt. So to get dt, we differentiate both sides. So it differentiates both sides. So you end up with dt is equal to dx on the square root of 2 sigma. Reason why is this here, you could say is x on root 2 sigma minus mu on root 2 sigma. This here is a constant. Derivative of a constant is 0. And here the derivative of x is 1, so you have to provide the dx on root 2 sigma, right? So here you want to get dt, so you want to get rid of dx, and that will be trying to get rid of the dx on top here. So we have to get this equation in terms of dx. So you carry across that, so you end up with dx is equal to root 2 sigma dt. So far, we know what we're doing to get rid of this here, to get the t squared in. We know what we're doing to get rid of the dx. But the last thing we have to do is if we change what we're differentiating or integrating in this case with respect to, we had to change the limits, which in this case was a on 2 to infinity, so you had to change it. So since t is equal to x minus mu on the square root of 2 sigma, so you can say when x is equal to infinity, t will equal to infinity minus mu divided by root 2 sigma, which will basically just give up to infinity. Because a very large number divided by a small number is still a very large number. And then when x is equal to a on 2, t is equal to a on 2 minus mu on root 2 sigma. So you have your limits. So we have your limits. You have dx, you have t squared. So we could plug everything into the original equation. So you'll end up, so probability x is more than a on 2 is equal to 1 on the square root of 2 pi sigma squared integral of a on 2 minus mu on root 2 sigma to infinity e to the minus t squared and you have dt square root of 2 sigma. So now we're seeing some stuff going. So we almost there. So this piece here, you could rewrite this. We put the square root over everything. So you'll end up with root 2, root pi, and the square root of sigma squared will just be sigma, right? So now we see how this will cancel with this, and this will cancel with that. So you'll end up with, so I'm telling you, pH, the probability x is more than a on 2 is equal to the integral from a on 2 minus mu on square root of 2 sigma to infinity of e to the minus t squared dt, and I'll write the 1 on root pi outside. So you have this. So if you compare this here with the equation for earth C on top here, you will notice that there's half, which is true. It is half because you're only using one piece. So now we could write this probability of x being more than or equal to, sorry, more than a on 2 would just be a half of earth C, and the x in this case is the point you're starting from, which is always going to be this bottom piece here. So a on 2 minus mu 1 root 2 sigma. And that is the answer. So it's basically as the UFC proof all over again. So it's the UFC proof. Make sure I know that proof. Okay, you need that proof for 21 and 22. And basically any normal distribution question this chooses to bring, you need to know that proof. You need to, because it will come. It will. Even the if you do the if, see the if is the same thing. Okay, just change the limits. Instead of going from x to infinity, or in this case a on 2 minus mu on root 2 sigma to infinity, or that be going from mu to x. Because I what if is, and everything else will be the same. Limits, yeah, differentiate t square, everything is the same. Because it's the same equation. If you look at it, if and if c is the same thing, it's just the limits different. And that's the proof. Alright, and then the last question of the night, E. So E, the noise voltage is amplified A times, and a positive DC component, B volts, is added to it. So let me just simplify this a little bit. So initially, so that before we do anything, your Y is equal to AX, sorry, that's X, that's by X for now. So you gotta write something initially. So you can say Y is X. So you have the expectation of X. So after you do all your tralala and whatever, so you're gonna end up with, you say U is equal to A, because it said amplifying it, AY, amplifying it A times, and you're putting a DC component to it, plus B. So you don't need to write this if it's confusing, because you don't write it. But basically, this is what it is. U, or whatever letter you choose, will be amplified A times, and you put a DC component to it. So that is what you have here. So the first thing you have to do, because it say write an expression for the PDF of the modified noise voltage, and the way to sketch the PDF, and the way to calculate the mean and the variance. So a lot of things we do. So the first thing we'll do is calculate what the expectation of U is. Right, so it'll just be the expectation of AY plus the expectation of B. So this here will just AY, the A will go outside, and the expectation of Y is just me. That is here, that was centered above. So you'll just end up with A mu, right? And then the expectation of a constant is the constant itself. So that's where your mean expectation is. Here's the first part. Then you have the variance of u. So that'll be the variance of ay plus the variance of constants. So the variance of ay will be a squared var x, and the variance of our constant is 0. So var x is sigma squared. So you just end up with a squared sigma squared. So as I mean, you have a variance. So now we could do what they want us to do. So they said write an expression for the PDF of this modified noise signal or voltage. Sketch the PDF function and we already calculate the mean and the variance. So we just write up here. So we'll write 1 and you can write the other one. So you can see the change. So if you amplify it, it will get higher. And if you shift it positively, you'll just move in this direction. So you just end up with it looking like that. So the red is the new one. So centered at A mu plus B. And you shift it across. So the purple, so you write the red. You have your shifting piece. So you have your variance. Yeah, so you mean your variance. You can write your axes just in case. So f of x and x. And the PDF to finish it off, f of x 1 on the square root of 2 pi sigma squared e to the minus x minus mu squared on 2 sigma squared. So now you know what sigma squared is and you know what the mu is. So all in all, you will end up with f of x 1 on the square root of 2 pi sigma squared is a squared sigma squared e to the minus x mu is your a mu x plus b squared divided by 2 sigma squared is e squared sigma squared. And that there is the end of this here. And that is the end of it. Alright, so